Solution equilibrium. We've discussed the equilibrium process involved in evaporation of a liquid into the gas state. And the idea of a solute dissolving in a solvent is very similar to that. So initially, the rate of it dissolving is much higher than the rate of recrystallization. Just like initially, the rate of evaporation was higher than the rate of condensation because there was nothing to condense. Here, there's no recrystallization occurring because there's nothing dissolved yet. So all we have is dissolving. As you get more and more solute that's dissolved, then the rate of recrystallization increases. And we get to this state of dynamic equilibrium when those rates are equal. So, as an example, sodium chloride. The sodium chloride is dissolving into aqueous sodium ions and aqueous chloride ions. But these ions can recrystallize to form the sodium chloride again, and they will. And so we have this reaction going in both directions. Dynamic equilibrium is when the rates in both directions are the same. Any questions? So here's the picture. There's our sodium chloride crystal. There's no sodium ions or chloride ions here, and so it can't crystallize. All we do is dissolve it. As these ions dissolve, now we get these ions in solution, and they can recrystallize. Remember, they're just kind of moving around, and if they bump into each other and bump into this crystal, they can get trapped in the solid again. And so when we get to dynamic equilibrium, we still have this solid sodium chloride here, and part of it's dissolving and part of it's recrystallizing at the same time. But the amount of sodium chloride that's in the solution is going to be constant. That's called a saturated solution. The water is full. It can't take any more. But as some recrystallizes, then others can dissolve again. Any questions?
Do we eventually get to the point where there isn't really like a solid mass? It's kind of just a bunch of the sodium chloride on the bottom.
That's a good question. Would you end up with just a bunch of little teeny tiny crystals or individual units on the bottom? Actually, no. What tends to happen is in the recrystallization process, the crystals actually tend to grow larger. Yeah.
So is that why mixing and dissolving things sometimes takes a long time? It's because it has to wait for some of them to pair back up so that others can fall apart? Is that what you're saying?
Well, dissolving is going to take some time because as these sodium and chloride ions are solvated by, through the ion dipole forces with the water molecules, they have to move away so that new water molecules can come in, right? It requires a certain number of water molecules to solvate a chloride ion. And another chloride ion can't leave until new water molecules have come in. And so especially if this is cold and everything is just moving slowly, it's going to take a while for these to just naturally move away. Now, if you put a stirring rod in here and stir it up, that's going to cause a constant flow of free water molecules to come in here, and things are going to dissolve more quickly. If you've ever put sugar in tea or tried to dissolve sugar, for Kool-Aid or something, it happens a lot faster if you stir it, right? If you just put the sugar in there and wait, it will eventually dissolve and mix, but it's going to take a long time. I mean, it could be days before it mixes thoroughly. We have some qualitative terms to describe solution. Saturated and unsaturated. So in a saturated solution, the word saturated implies that something is full, right? The solution is full. It can't hold any more. And so the dissolved solute is in dynamic equilibrium with the solid solute, and if you add more, it's not going to dissolve. You can only dissolve so much sodium chloride in water. It's quite a bit, but there comes a point where you're limited, and so that's it, saturated. Unsaturated means there's less than that equilibrium amount. If you added more salt, it would dissolve. So, you put a teaspoon of salt in a cup of water and you stir it up, it dissolves. It's not saturated. It's an unsaturated solution. You could put another teaspoon of salt in there, stir it up, it'll dissolve. You could keep doing that and keep doing that. Eventually, you'll get to the point where you put salt in, and no matter how long you stir it, it will not all dissolve. That's a saturated solution.
I'm gonna assume it's the heat, right?
The solubility depends on temperature.
So is there a point where you could make it like super hot and stir in continuous stirring and it still won't dissolve?
Yes. There comes a point, even at a high temperature, where, yeah, there's a limit to how much will dissolve. And that limit depends on the individual compound and on the solvent itself. So we have saturated and unsaturated, and then we have supersaturated. A supersaturated solution contains more than the equilibrium amount. Does that sound crazy? You've dissolved more than you can dissolve. How is that possible? Temperature. So a supersaturated solution is formed by heating. At a higher temperature, the solubility increases, and so you can get more to dissolve. And then if you let it cool down slowly without disturbing it, you can kind of fool the solution, and it'll remain in solution until it's disturbed. It's a little bit like, the cartoon characters, they run off the cliff, and they don't fall until they realize that they're standing in air, right? So a supersaturated solution is like Roadrunner didn't go off the cliff. It was always Wile E. Coyote, right? The supersaturated solution is like Wile E. Coyote who has run off the cliff. And when you disturb the solution, it's like telling him, hey, you're standing on nothing. And he's like, ah, and then he starts to fall, right? Okay, so I have a couple of videos for you. Well, that's usually the one I'm familiar with is exothermic, and so it gets hot. So let's see if I can get this to play.
Kind of cool to put your hand in there.
I'm going to pause this because this is not. So here's a graph showing solubility versus temperature. And we see that the solubility of most solids in water increases with increasing temperature. So you look at potassium chlorate. At 0 degrees Celsius, it's almost insoluble, very little bit. So solubility here is grams of solute in 100 grams of water. So you could dissolve maybe 3-4 grams in 100 grams of water, in 100 milliliters. You get up to the boiling point of water, and now you're up to like 56, 57 grams will dissolve. And so we see that most of these have a curve that goes up, right? Sodium chloride is not very temperature dependent in its solubility. It'll dissolve a little bit more at the boiling point than at the freezing point, but not too much. And then there's sodium sulfate. Somebody's got to be weird. Sodium sulfate becomes less soluble at high temperatures. It's not what we expect. Recrystallization is a technique that can be used to purify a solid. So what you do is you make a saturated solution at a high temperature and you let it cool down slowly. Most solutions will not be a supersaturated solution that'll precipitate all at once. Usually what happens is they will slowly recrystallize. What happens is that as the crystal begins to form, it is energetically favorable to have a perfect crystal, where you don't have any extra things in there, no dust, no extraneous particles, and they just form a beautiful, perfect lattice. And so when you let the crystals form slowly, the structure tends to reject impurities, and the crystal you end up with is larger and more perfect and purer than what you started with. And this is actually a picture of rock candy, which is made by recrystallizing table sugar. I have never, not that I've devoted much time to it, but I remember trying that as a kid, and it didn't work at all. So if you want to try that, I would encourage you to look up some instructions. Save yourself some time and learn from other people's experience, but it certainly can be done. You heat up a solution, takes a lot of sugar, because sugar is very soluble at high temperatures, and then you let it cool down slowly. Solubility of gases in water, gases behave differently. Water contains, like the tap water, contains dissolved air. That's why when you heat water, you know, maybe you've noticed when we've heated beakers of water, you see these little teeny tiny bubbles and you think, oh, it's going to boil. And then you're like waiting and waiting and waiting. What you're seeing, the little tiny bubbles, is dissolved air coming out because air, gases, are less soluble at high temperatures. And we know that from experience. Here's someone pouring cold soda and warm soda. If you open a warm 2-liter bottle of soda and pour it, we know from experience you're going to get a lot of foaming and fizzing.
If there was ice in the cup, but you poured the warm soda in that cup, would that make less bubbles?
I think having ice in the cup when you pour the warm soda would help, but you're still going to retain more fizz if it's cold to start with. So as the temperature of the solution increases, the solubility of the gas decreases. And this has a big impact on aquatic life. You know, fish require oxygen to live, but they don't breathe air. They get the oxygen out of the water. There's dissolved oxygen in water. At higher temperatures, there's less oxygen. We had some goldfish when we first moved to the valley, and, you know, the average temperature in the house, you know, the temperature of the water was like 80 degrees in the summer. And these poor goldfish are at the surface just gasping for air. And I looked up all kinds of stuff because I didn't want to torture the goldfish. And I found out that they will acclimate after a while. But goldfish would prefer the temperature to be more like 75 degrees. I'm not going to run the AC for these goldfish that we got at the street fair, right? Not going to happen. So we threw ice cubes in there to help them out a little bit, and eventually they got used to it. Yes?
Is that why, like, up and down the coast, like with Monterey, the waters, the oxygen level is really rich, like, or does it matter, just like the colder the temperature, the richer?
The lower the water temperature, the more oxygen will be dissolved. Yeah. And so there are cold water fish and there are warm water fish. And a cold water fish will not thrive in warm water. They'll die because they just can't get enough oxygen. So they basically suffocate. And so you get problems in lakes and rivers if there are factories that are dumping warm water into the river. The water may be clean. It's not a chemical pollutant, but they're dumping warm water into the river. That affects the oxygen levels for a big part of the river and will kill off the fish and other aquatic life.
Will warm water fish do fine in cold water?
Warm water fish have a problem in cold water, but it's not because of that there's too much oxygen, but their bodies are used to functioning at a higher temperature. And temperatures affect the rates of reactions. And so their bodies have enzymes and different processes that require a higher temperature. And because fish cannot regulate their own body temperature, they're dependent on what's outside.
A lot of it's hypothermia too, because I had beta fish and I left for a couple days and it got so cold in our apartment that they literally just got too cold and died.
Yeah. And so, you know, warm-blooded mammals, we regulate our own body temperature, and so we can handle much greater swings in temperature. But if your internal temperature gets down like 90 degrees, you're going to die. It's not that you've frozen, but all of the chemical processes, chemical reactions going on in your body slow way down, and so you're not going to get enough energy to your brain and things die. Pressure also affects the solubility of gases. If the pressure of the gas above the solution is larger, the gas will be more soluble. And we see this with soda as well. And this is really making me want a soda. So you open the can of soda and you hear that psst sound, right? Pressure being released. They can't fill the soda can all the way to the top. They need to have a little space, and that little space up there is filled with carbon dioxide under pressure. And when you open it and release that pressure, then the carbon dioxide begins to bubble out of the solution. You can do this with like a 2-liter bottle, clear plastic. You release the pressure and watch, and you'll see bubbles start to form immediately and start coming to the surface. Because now you've reduced the pressure and the solubility goes down, so it begins to come out. So that's why if you want the soda to stay bubbly, you need to put the lid back on, right?
And that's why it tastes flat after a while too.
Yeah.
Like,
Soda goes flat because the excess carbon dioxide has come out. Now, could you recarbonate it? Yeah, you could. And now they sell those, I've forgotten the name of them. They sell these machines that you can make your own soda at home, right? And they use pressurized carbon dioxide to dissolve more carbon dioxide in the water.
Sounds healthy.
Well, carbon dioxide is not harmful.
And if you're drinking soda, you might get
Yeah, if you're drinking soda, you're not too worried about that. Yeah, we're gonna do a calculation hopefully today where we get to the amount of sugar in soda. It's alarming.
It's very.
So here, if we have an equilibrium, we've got carbon dioxide in the water and we've got carbon dioxide above. If we decrease the volume here, we're essentially squeezing these carbon dioxide molecules closer together, and that will increase the rate at which carbon dioxide dissolves in the water. It does nothing to the rate of evaporation, or it's not really evaporation, it's I've lost the word for that. Dissolution, I guess. And then it will establish a new equilibrium. And so now the pressure here is lower. So if we pump more CO2 in here, that's going to essentially force carbon dioxide into the solution. There's an equation, of course, to relate that, is called Henry's law. So the solubility of a gas in a liquid equals a proportionality constant times the partial pressure of the gas. That's the partial pressure of that gas above the solution. So the solubility for gases is usually given in moles per liter. Oh, there's a typo. That's supposed to be a subscript. KH is Henry's law constant, and so you would just look that up. You don't memorize that. It's usually in moles per liter per atmosphere, and then the pressure of the gas is usually given in atmospheres. So if you take a bottle of soda and you use one of those devices they used to sell on TV to pump a bunch of air into the half-empty soda bottle, is that going to affect how fast the soda goes flat?
Normal air?
Just normal air.
I would say
It'll affect it, but not very much. The amount of carbon dioxide in the air is about 0.6%. Very little carbon dioxide. What matters here is the pressure of the particular gas. So if you're pumping in nitrogen and argon and oxygen mostly, that's not going to affect the carbonation level of the liquid. It's got to be the gas that you're interested in. So we should be able to do problems like this. Determine the solubility of oxygen in water at 25 degrees Celsius exposed to air at 1 atmosphere. Assume a partial pressure for oxygen of 0.21 atmospheres. So normal air is about 0.21 atmospheres of oxygen. Well, we need the Henry's law constant. So for oxygen is what we're looking at. Henry's law constant is 1.3 times 10 to the minus third. So KH, what did they say, 1.3?
Yeah, times 10 to the minus.
Times 10 to the minus third. And that's molarity per atmosphere. So the solubility of the oxygen is going to equal the Henry's law constant times the pressure of the oxygen. So 1.3 times 10 to the minus third molarity per atmosphere times the partial pressure, 0.21 atmospheres.
Is that just the percent of oxygen in there?
Yes. The percentage of oxygen in the air is about 21%. And if the total pressure is 1 atmosphere, then 21% of that pressure is due to the oxygen. So the oxygen partial pressure is 0.21 atmospheres.
Connecting classes, right?
Yes, connecting sections. So I'm getting 2.7 times 10 to the minus 4 moles per liter, because the atmospheres cancel out. Minus 4. So water at room temperature and atmospheric pressure doesn't have a lot of oxygen in it. Any questions?
So solubility is just the molarity?
Solubility will be expressed in some sort of a concentration unit. Yeah. And for gases, it's usually moles per liter. For solids, a lot of times it's grams of solute per 100 grams of solvent.